Hello guys, welcome back to another video. In this video actually I'll be discussing with you this challenge that I had talked about in my first or second video, I guess. So this is the challenge that I had participated in. It is basically called ICDEC 2024 challenge on vehicle detection in various weather conditions. So this was also sponsored by the third international conference on data electronics and computing on this date in Turkey. So here is a quick introduction about this. Nowadays the constant growth of number of vehicles on the road has led transportation officials to look for more effective solutions to alleviate the problem of traffic congestion. So basically we have to develop a AVD system known as automatic vehicle detection system these AVD systems detect vehicles present in certain areas. So basically if you see nowadays there are self-driving cars, like the most relevant car or company you can say in this field is Tesla. They have these cameras in their cars, and those cameras capture a video. Those videos are then analyzed frame by frame by the machine learning model that is present inside the car's computer, and then based on that it actually infers whether the object in front of it is a vehicle or if it is a traffic sign, or what kind of vehicle is that, how away is that, and all those things. So that is basically what an automatic vehicle detection system means. And we'll have their images captured from cameras installed in vehicles that can be used for precise vehicle detection. I just discussed this. And the thing about object detection is that we basically focus on the region of interest. So after removing the background and undesirable portions of the input image, features are extracted. By features I mean the region of interest. Like in a photo there might be many things, but the actual region of interest lies in the vehicle objects, or maybe traffic signs, or maybe road symbols. So the features, these things are called features, and they must be extracted. These features may include the shape, color, texture, or visual characteristic of the vehicle as the region of interest. So there are these things that can be attributed as characteristic for the region of interest while developing these systems. So these ROIs are used to detect discriminative features to achieve better recognition accuracy. So these ROI actually help us to recognize these patterns much better as compared to any other techniques or algorithms. So this is what AVD and ROI is. So this is just the schedule, the registration opened and all that. This is the registration link. It's pretty late if you want to participate right now, but it's fine. I've already participated in this. These are the awards. The first place, the team that will come at first place will win this amount, and then this, and the third one will get this. All those three teams will also be invited to contribute to the competition summary paper, which will be including the proceedings of this one. And the top 5 participating teams will receive certificates from this committee. So let's go to the competition outline. Over the years, vehicle detection has predominantly been conducted on videos captured in actual or various weather conditions. However, there is still room for improvement in vehicle detection in various weather and lighting conditions. So of course, the traditional models, I will come to that part later on, but let me just give you a gist of it. I tried using the state-of-art YOLO V8 model, the pre-trained one that comes with Ultralytics, and I tried to validate that model on the dataset provided by this competition, but actually it performed very poor, like very much poor. So however, that was understandable, like it was not fine-tuned for this specific data set, but still it should have performed better. Yeah, so furthermore, various videos are being captured for the detection of the vehicles, and the features of the vehicles including shape, color, texture or visual characteristics are being extracted based on region of interest and classify them into different vehicle types. So the dataset we have comprises of 3200 images of vehicles captured under various weather conditions. So they have already released the dataset where out of 3200, 2600 images are for training and 200 images are for validation. All images are also annotated in the YOLO format, that is the class ID and then width, height, and all those 4 other coordinates that actually specify the bounding boxes along with the class ID. So that is the format of annotation, and these annotation will be provided for both training and validation purposes. So that's fine, and each team can have up to 4 members. Basically my team has only 2 members. There's me, and then there is another friend of mine who is from another college. So we're basically working on the system, and it says then if a team submits more than once, the organization will consider the last submission as the final entry. So we are basically trying to make train multiple models, so that to basically find which one works the best. We are initially just fine tuning the models on this specific data set, as me myself I don't know how to write the models from scratch right now. I'm not that good in this, so I'll just stick with fine tuning and changing all those hyperparameters and the augmentations and all those stuff to improve these matrices like this map score and the F1 score. So we have to make all this GitHub link of the proposed model and then a concise one-page report outlining the methodology that we employed while training this model. And yeah, there is that. So now let's move on to the dataset. Let's just quickly visit this one. Yeah, so as you can see, this is an image in a harsh weather condition. This is rainy night, and there are cars in here. Like here you can see there is car over here as well. However, it is not, you cannot see it properly, but it has been annotated. So, and you can see the bounding boxes are also colliding over here. This bounding box is totally inside this one, and out here the bounding boxes are colliding as well. So, and the quality of images are not that good either, as you can see over here as well. The bounding boxes are provided here. So yeah, this is the overview of the dataset, and then let's move on to the dataset GitHub repo so that we can actually see the dataset. So this is the format of dataset that we have been provided. The readme file just contains info that we just read on their official website, and here you can see there are 3 directories: annotation, train and val, and then this is just readme.md. So inside the annotation we have got the train directory and val directory. Inside this we have rainy directory and sunny directory, and inside both of these we have day and night directories, and each of these directories contains the obj.data. The obj.data just contains some info about the annotations. I don't know yet what to do with these. Actually I tried, I firstly went with the YOLO V8 model, and that model didn't require me to have all these. These are the list of all the class names that are in this. There are actually many discrepancies in this data set. I have personally opened 2 different issues regarding this, and I'll discuss with them with you one by one. Let me just open one of the label files. Here you can see this image has all those 7 labels, 7 different bounding boxes are there, and then all those bounding boxes belong to class 13, class ID 13, and these are the coordinates, those 5 coordinates representing the values, the bounding boxes. So here is it, and at the last you will see this train.txt file. It basically contains I guess it links all these txt files to the JPG their JPG counterparts, like the image files. This basically acts as a link to them. Yeah, so this is the format. Now let's move out here and let's see one of the training images. Here is rainy, then similarly day, and then look at this photo. This is one of the photo. So if you just basically this dataset is not very diverse. In a sense, I'm saying that look at this picture here and then look at this picture over here. So if you go on moving picture by picture away, you will basically see that all these pictures, if you basically here rainy day 1 is there and then rainy day 2 might be somewhere else. So if they were sequence, you might be able to see that all these pictures are actually extracted frame by frame from a video that was captured by some person moving on a vehicle. So there is this background as well, and it is basically very tough to perform trainings on this sort of data set. So there is this, and now let's moving on to the issues that I had faced. All these images are like this only. They are all extracted from a particular video by splitting it frame by frame. So now let's finally move to the issue section. So this is the first issue that I had noticed. So I was trying to train the model on this data set. I basically had to convert the data set that was in this format to a data set that was compatible with training with YOLO V8 or maybe YOLO V5 model. I had also trained it on YOLO V5, then I moved on to the YOLO V8 model as it was more recent, and I guess it should have done better. It did not, although, but anyway. So this is an issue that I'm talking about. Like the dataset provided has annotations as well. So obviously the competition has provided us with annotations. So if you go with on this, or maybe this particular file had this issue, so I had to debug this while training. So while I was training, I got this issue. I got this error message in the this one, train warning, one duplicate labels removed. So this label basically was duplicated. As you can see, this one and this one are essentially the same thing, but it was repeated once again here, and I cross-checked it in the official repository over here, but it was like that here as well. So I asked them to remove this. It might not be causing some error over here because it is basically YOLO V8 model is very robust, and there are many exception handling and error handling modules in this. So it can work scalably and robustly in all these situations, but it might not be the case with other models. Like if you go with efficient detection models, efficient det models, they don't have those many features, like and they aren't that much user friendly as well as this YOLO V8 model that is implemented in PyTorch. So what I want to say that it might cause some issues there. So yeah, it should have not been there in the first place. And then there's this issue opened by someone else. He says that improper annotations are there, the bounding boxes are not accurate, a lot of classes are mislabeled. So I did not have the opportunity to go through each of the images one by one and check if there were any mislabelings, but if he's saying it must be true to some extent, the bounding boxes are not tight, or maybe he wanted to say right. So there's that. And then there's this issue that C faced and I had also faced, but I had to debug it manually again. So C says that there are two issues with the annotation. The class number is given as 40 in several files, which is causing an index out of bounds error because the number of classes is only 40, assuming the class number should be from 0 to 13. So as I showed you in the in this, let me just show you again. Annotation, and then train, and then rainy, and then day. And now if you go over here, you will see that only 14 classes are there, but I actually am forgetting the exact location of that file, but I guess in some other folder it was, the number of classes were 15. So there's this issue again, that some of these directories have only 14 classes and then some have 15 classes. So if you try to train all these images, or maybe feed all these images to a model, you have to collectively feed those images and not class wise, because this is an object detection model. The class wise labeling is already done in the annotation. There's no need for this this classing, this day and rainy and all that, those classing labelings. So there's this issue that I was talking about. So I just mentioned it to her that there are actually 15 classes, not 14, and I also faced this issue and had to debug this. So in some file it is mentioned that the 15th class is there as well. It is known as cycle van. It might be some name they came up with, because there is this rickshaw like vehicle which looks like a van but is also a cycle, so maybe they named it cycle van. Here it is. It is not in all of the folders, so that's why she might have faced that issue, and I also faced that. So there is that. Yeah. And then I opened another issue where I explained that the number of instances, this is the one of the most major issue, the issue that affected the training the most. Any model that is supposed to be trained on a data set must, if the model is complex enough, it must have enough data set, and the data set should be large enough in order for the model to actually understand and reach the convergence point. But here, as you can see, I wrote a script and ran it on the dataset, the raw dataset that we were provided with, and I actually counted all the labels, like the number of instances. The car was there in all these images, and then bike, and similarly like that for all the classes. So as you can see here, the class counts came out to be 10,000, around 10,000 for car class, and 2,300 around something for bike, and then 1,000 for auto. And then as you move down, you can see the cycle van had only 45 instances, and then motor van had only 9 instances, and the train had only 2 instances. Now you tell me if I'll ever be able to make a model to be biased towards this train, which has only 2 images, and there is another restriction with this competition, that we have to strictly train our model on the provided dataset only. So it is not like I can come up with another image from internet and train my model with those images. So I'll have to do something with these 2 images only. So I came up with an idea, and I oversampled, I just copied pasted the instances that had lower representation like train and all. I wrote a script that accepted distribution, and I oversampled them one by one. And finally the number of instances for each of the classes were somewhat respectable, although one image might have more than one class vehicles, like there might be car and then there might be cycle in the same picture. So if I have to oversample cycle, the car will be oversampled by itself, and the number of instances of car will also increase, even though it already has so many instances. So that is something that I cannot control. And so this is the last issue that I opened. And now moving on to the solutions that I have worked on. So let me just show you. I had tried training YOLO v5 model on this dataset, and then I tried training YOLO v8 model in this dataset, and also the FDET model. Let me just move you through all the solutions one by one. So this is a checker.py. Let me just open this in my VS Code so that I can show you all the script files that I had used. This is the YOLO v5. Yeah. So I have actually removed the dataset. The dataset was just the same that I used with YOLO v8 initially. So let's just stick to the scripts that I've used. So this is a annotation checker script. It will basically check if all the annotations in the dataset are fine or not, and it will basically check that only. So and then there is this checker.py. It will actually check for invalid labels. I had actually, the first issue that I had opened on that GitHub repo, I found that issue using this script only, and it found out that that one label was being repeated again and again. So and then this cleaner.py. So basically it removes all those white lines that are that are somehow incorporated by some mistake, or I don't know, whatever. And then there is this driver.py that basically is used to train the model. And then this is the script that I had used. I kept the batch size 4 because there is this bug in the Ultralytics models, specifically with the YOLO v5 and YOLO v8 models, where if you keep the AMP attribute as false, those map scores as well as loss scores become nan. So and the training simply does not happen. So yeah, there's that issue. And yeah, that is everything in this. And now let me check if so there is this runs, and inside this I have the YOLO. Here you can see the results. I trained these 3 different models. No, actually it was the same model, and I had trained it 2 times. So this is the first one, and here you can see there is no confusion matrix and all, maybe because I had prematurely stopped the training process. As you can see, I had stopped the training process at 35 box only. So let's analyze this. The training loss, box loss, started from 1.9 and it went down to 1.5 through 35 epochs. The class loss went down from 2 to 0.82. That's significant as compared to the box loss, and it was significant in all the trainings that I had completed. So class loss was comparatively decreasing much faster as compared to the box loss, and this DFL loss had also increased, but very, very slowly, 1.2 as compared to 1.1. The precision initially was 0.31, and then it went to around 0.59 somewhere, and then 0.60 as well, and I guess that is the highest it went ever in the 31st epoch, and then it again reduced down to 0.38. The recall metrics started from 0.26 and it went to 0.29 when it had the highest precision, which is not so great. It had other higher recall values as well, like this 0.37, and I guess that is the highest it ever went. And then map scores were 0.35 at the end. It started from 0.2 and went to 0.35. It even went to 0.36 or 0.39. If you can see, it even went to 0.4 over here. And then the map scores for IOU 50 to 95 started from 0.07, went all the way to over here, and these values were again nan. So as you can see, the improvement was not so great. For example, let me just run a validation script for this. I guess it will show you how good it worked for all the classes. Let me just copy this and I have the validation script in this file and then paste it over here, and then let me first run this. Open the folder of YOLO V8. Yeah. So here is the file and validate.py best. Yeah, so it should work, I guess. Yeah, so as you can see, the model scored 0.438 of map score in IOU 50 and 0.223 in IOU 50 to 95 with a precision of 0.645 for all classes. And as you can see, it was also expected that car had the most number of instances, and hence it had the best precision and recall values as well as highest map scores for all the two of the IOUs. And then if you move on to the train class, it seems like train class is not here. Yes, so it's not here. So if you look at cycle, then you can see here the precision was 0.405 and then the recall was only 0.087. The map scores were pretty disgusting, and yeah, so this is the score that I got while training YOLO V5 model. So I didn't actually, while training the model, it came to my mind that it would be better if I went with YOLO V8 instead of YOLO V5. Initially I thought my system might not be able to handle YOLO V8 for training purposes, but I found that it was even more efficient than YOLO V5 in terms of computational resources. So yeah, so that's why I moved to YOLO V8 from YOLO V5. Now that I have discussed the results from YOLO V5, now let's move on to the YOLO V8, and there are basically many scripts over here. As you can see, let's just remove this now as we don't need it anymore. And you can see there is this augment.py. I am using image aug library. This is an open source library that is mostly used in augmenting the data sets in machine learning models. So I also tried to use the I won't say much better because it didn't work for me. There is another library called Albumentations. It is another library used for augmenting your data set, but it actually didn't work. I initially was facing the normalization issue where the coordinates of x and y's were not in the range, or were not being normalized in the range of 0, 1, even when I was explicitly trying to normalize them. And then I had to debug this issue all night so that I can finally augment it. And I went through all those forums and whatever, but I finally eventually came with a solution that replacing the parameter in the albummentation script of bboxutil, where it actually checks for the bbox's coordinates, whether they are normalized or not. I had to change the format. It was somewhere. So it was some different script. It was different from this image aug. And there is a place where you actually specify the format of bboxes, and it was initially YOLO, and I had to change it from YOLO to Pascal_VOC, Pascal walk, so that that normalization issue was gone. Like I didn't get that error anymore, but then I faced another error. Let me just show you that too real quick. Xmin, yeah. So it was something like this: xmax is less than or equal to xmin for bbox, and I got some similar errors for y coordinates as well. And if you go through all these forums, like here, he got this issue, and he was he was basically able to fix it by using this snippet, not by using this snippet directly, but he was able to diagnose it, but this was not applicable in my case simply. And then there's this issue in the GitHub forums of official GitHub implementation repo. Some guy also faced this issue, and he just I don't like him. He just said simply, this is an annotation problem, some B boxes are empty, instead of explaining anything further. He didn't even try to analyze it, I guess. So revisiting the thread, for some experiments we would like to train with hard negative method. For including those in the training is to have boxes with all zeros. For example, this is suggested by the author of efficient det. So I don't know, I didn't try the augmentation yet with efficient det models, but maybe it might come in handy if I try that. So this is all this GitHub had to say. And then there is this, some other guy also faced this issue, and seems like he's not able to understand that either. So let me just remove this. It might be narrowing down my search results much more. So okay, yeah, this is the same one that we just visited. And then there is this one. Yeah, so this is the one where I actually found the answer. So this guy was also facing the same issue, and then he's just telling him to use markdown messages so that it would be much more understandable. I think his native language is also not English, because you can see that is apparent. And he gave us a solution that we have to do this we have to do this while normalizing or augmenting the B box coordinates, but I tried this and it didn't work either. So, and then this guy gave this solution to this. He said that I had to add this append this code block into this function, which is there in the official implementation installation site and this script, but I tried that and it didn't work either. However, many of the people found this solution to be working, and they're just thanking him and all. And this, as you can see over here, this issue arose in 2019 and it is still prevalent in 2024. So it's been 5 years and the issue is still there. So I don't know why. So I finally decided that implementation might not be tool compatible for me for this purpose. So I switched then to the image aug, which I guess was much easier to deal with. It's a straightforward code where all those images and boxes are loaded, and then this is a function for saving those augmented images. This is the function where I actually augment the images, and as you can see here, the boxes are being normalized, and over here I'm using all the API keys that are used for augmentation, like this. Flip LR will horizontally flip the images with 0.5 degree, and then multiply. It will basically multiply all those images randomly within this range value, and it will basically increase or decrease the brightness of the images. And then there is this affine, and then there is this additive Gaussian noise. This will just add some noise to the images so that it could be understood better. And I guess I also trained the model today for I don't know, maybe 7 to 8 hours, but the model was not doing much better, and I guess it might be partially because I had applied this this augmentation technique called cutout. It basically cutouts a portion of the images randomly from anywhere, So I saw some images and it was like, let me just show you how that was actually like. No, I guess it is not there. I deleted that folder. So actually it was causing me some issues while training, because it was actually also removing the relevant parts of the images, like those region of interest I was talking about. Let me show you. What was it called? It is called cutout. Yes, HOG cutout. If you see the official documentation, you will find various API keys that are there, and multiply cutout. Yeah, so here it is. As you can see over here, these random sides of the images are being cut out, completely cut out. And this was actually like, for example, if these two cutout portions were over here and here, it might be actually very difficult for the model to understand, which is all, and the understanding process of the model is already very much affected by the quality of dataset we have been provided. So adding this augmentation might not be a better idea. So that's why I have commented this portion out, and I'll try using the augmentations again with some another combination of these API keys. And yeah, so this is the augmentation script that I used. And then there is this checker.py. It basically checks if the labels have any issues, like for now the dataset, the directories are pointing to this. So let me just show you how many instances are. Yeah, so this is the script that I used to check how many instances of each class were there, that I had used in opening that issue in the GitHub repo of this dataset. So let me just quickly show you. Yeah, so as you can see, there are 67,930 instances for car, and for boot it is this much, and for train it is 2501. So this you might be thinking, where how did I get these many instances? But I just copied the instances where trains were there, like for example initially it was 2, so the copied images must be at least 2500 by 2, so it was copied 1250 times at least, the train images, the images containing trains. So that's how it the number of instances increased to this much. Initially the number of instances were this much, and now it is this much. But I tried to train the model on even this oversampled dataset, but that didn't help much either. So, and this is the distribution that I used. This has nothing to do with the actual. Even if I remove this, nothing will be affected. This is just redundant part of code. It was actually used when the actual data distributor script worked. Here it is. So the number of instances of car was already 10,000, and I actually needed all the dataset, as it was guided in the rule book that it is mandatory to train our model on the given dataset only. So I was not able to remove the instances of car that was already there. So I just upscaled the number of instances of other classes, like all these I brought it up to 2500 number of instances, and then I just ran this script, and boom, all those images who were undersampled or underrepresented were copied. And then this detect.py, it is basically used to perform inference via a trained model on a video file. So let me show you if I can the output is over here, clips, and yeah. So actually I don't know why, but VLC just gets hung up whenever I open this output media. Is it running? Yes, it's fine. And if I open with another file like this, it just runs fine. Here you can see some of the cars are being detected, but they are still being mislabeled, like you can see over here. This one is detected as truck, and this one also as truck. No one is being detected as car, and instead of all these vehicles being detected as car, only some of them are being detected. So of course our model is not good. This inference was done on the first training of the YOLO V8 model, on the initial dataset that I had before augmenting or oversampling it. And this is oh my bad, I did the same mistake again. And this was the file. This is the inference that I got from after oversampling the images. And let me open it with videos again. Yeah, you can see the performance even got worse. Yeah, it might not be worse, but it is not good either. And this is the original video. Nothing here to see. Yeah, so these are the inferences that I got. So this is what basically this script does. And there's this label checker.py. This again checks if any label has only four different attributes for a single label. Like each label must have 5 different attributes, that is class ID and those 4 coordinates to actually define the bounding boxes. So if a label has less than 5, so it will just give me this. I used this script because I was actually facing many errors while augmenting the dataset, or even when I was oversampling the dataset. So yeah, that's why I did that. And it also checked for any trailing spaces, or maybe like if some label has trailing spaces ahead of it, it was simply not detected while training the model. So I had to manually detect all such fault. Script basically checks all the labels that are there and finds if any labels are wrong. And there's this save.py. I just used it while augmenting the dataset via some different strategy, but that didn't work either. So this is another redundant script. And there is this test.py. This basically performs inference on a particular sample image using a model. As here we are using YOLO V8 n.pt. This is the default model that comes with YOLO V8 model. So, and there is this validate.py. This basically validates a model on our validation dataset. Yeah, so these are all the script that I had used now, and this is the main script that I was using to train the model. Now moving on to the results that I got using all this. So let me just show you it quickly. This is the dataset, and here you can see in the training directory after oversampling the images. From 2600 images we got 30,625 images, and then in the val we didn't oversample the val, it was not necessary. And then label also had 30,625 items. Yeah, so there is this is the dataset. And if you go over here, you will actually find, so this is the confusion matrix and all those weights for the first training that I did, and this is the confusion matrix for the first training. As you can see over here, the primary issue in while training the model, now we can discuss this. The primary issue with the training the model was that it was actually detecting backgrounds largely. As you can see over here, the true values is car over here, and the predicted value is car for 427 times. However, the true values was car and it was predicted as background for 315 times. So you can see how big of an issue this one is. And then if you see the instances of bike, there were total 97 plus 28 instances of bike, and it was correctly classified 28 times, and it was then again misclassified as background for 97 times. And you can see the same goes with each of other classes. They are all being misclassified as background. And then you can see over here the actual background was also misclassified as car over here for 175 times, and not even once for the actual, and the background was not even classified for once as the actual background. So the main challenge that lie ahead was to to make the model understand that it does not have to actually capture the background. So I didn't know back then what I was doing wrong, because we were already providing the model with the bounding boxes, and it had just to focus on those bounding boxes, but instead it was also focusing largely on the backgrounds of the images. And since the weather conditions were very bad, it was very poorly doing that, even the background classification. So, and then let's move on to this. This is just the probability matrix, normalized one between 0 and 1. And if you see, here is the precision curve. It is something like this. For some classes it is very much weird. And then this is the recall curve. It all converges to 1 down here. And if you see results, let me just show you. I trained this model for the first time on the raw dataset that we have been provided with, and I trained it for 50 epochs, and it started from 1.9485 box loss and came down to this. So the reduction was pretty minimal and very much slow. However, if you see for class loss, it was 2.82 initially, and it came down to 0.71. That was pretty big. And the precision also kept fluctuating, and all those things you can see. And it will be much more better if you see the result. Yes, you can see that loss decreased gradually. The class loss also decreased, and then it finally converged. The DFL loss also kept decreasing, but you see precision, it kept fluctuating throughout the training process. And then recall was also fluctuating pretty bad. The map scores increased up to a point, and then it just kept fluctuating. It increased up to a certain point, and then it came back, and then it just kept fluctuating. And yeah, so there is that. Now moving on to the second training that I performed. I actually continued the training process on the same data set, but I basically utilized transfer learning. I continued the training the data set from the last checkpoint that I had saved. And here even you can see the performance of car here is much better. It was correctly classified as car for 595 times and wrongly classified as background for 147 times only. And the same was with all the other classes. The performance was much better in this training session, as you can see from here as well. As you can see, cycle is still being largely misclassified as background. 0.87 of the total probability is still the background, so it is bad on that class. And here's the F1 curve, and this is the precision curve for this, and this is the recall curve. Yeah, so this was for train 2, and now if you move on to train 3, you can see again the performance started being poor. The number of instances where car was being mislabeled increased again, and it is also visible from this normalized confusion matrix as well. And the F1 curve was somewhat like this, and the precision curve was like this, and the recall curve was like this. Yeah, so if you see results.png, here you can see all the matrices in one go. The loss kept decreasing steadily. The class loss and box loss both kept decreasing, as well as the DFL loss. The precision, however, it kept fluctuating again very abruptly, and the recall was also fluctuating. The map score increased if you see these orange dots over here, but it was also largely fluctuating only for both the IUs, that is 50 and 50 to 95. And if you look at results.csv for this, I trained this. This is actually this is the third training that I did, and this was on the oversampled dataset. And as you can see over here, after 50 epochs, the loss was still very persistent, and the class loss, because I was using transfer learning, so now it started from this much only, and it reduced to 0.66, and the DFL loss was decreasing very slowly. The precision was also not that much great. It just reached, I guess, 0.54 max. Yeah, I guess that is the max it reached. And the recall was also not that impressive. Even the map 50 scores were not that impressive. As you can see, nowhere it reached even 0.3, so that's some poor performance. So this was it for train 3. And then for train 4, I actually augmented the images. Even you can see, no, actually I had not augmented the images yet. Even I had not oversampled the images yet. As you can see, the number of instances for all these are pretty low yet. And if you see the confusion matrix in this, the performance was still poor. So basically, in the first instance of training that I tried training the model on the raw data set, in the first instance when I trained it, the background was much better. Not actually in the first instance, it was in the second instance. When I used transfer learning, I first trained the model for 50 epochs in the first instance, and then I trained it on another 50 epochs in the second instance, and the performance was much better. For car, as you saw there, that car was largely labeled largely predicted as car only for most of the time, and it was. However, if you see, all the other classes were starting to perform much better as compared to previous performances. If you see the normalized matrix here, you can see cycle is still largely detected as background, and the car is also, yeah. So performance was overall not that much great in this training session either. The F1 curve was something like this, and this is I just showed you this, and the precision curve was like this, and the recall curve was like this. The results were like this. So the loss increased for a certain point of time, and then it decreased. Same with the class loss and the DFL loss, because I was using transfer learning, that's why the trend is like this. And the precision learning and the precision matrix was then again fluctuating very abruptly. Even the recall and map 50 scores were fluctuating. And if you see the results.csv file, you will find that I actually trained this for 136 epochs, and this training session actually stopped because the model was not getting better even after 100 epochs. So there is this checkpoint in YOLO V8 that is implemented automatically where if for 100 epochs the model does not improve, it automatically stops the training process. So the last regarding this information, if you see the last best metrics the model got was at epoch 36. This is that, and here if you see in the epoch 36 the precision was 0.47 and the recall was this much. The map scores were this and this, which is then again not that much great. So as you can see, even after training for so many epochs, it finally reached convergence and it was not getting any better. So then I finally thought of augmenting and oversampling the dataset, and so I did that. As you can see over here, I increased the number of samples or instances for each of the classes, and the confusion matrix that I got after doing this was like this. You can see not much improvement, right? The background is still being detected for most of the classes instead of the true labelings, and the precision curve was not that great either. Same goes for the recall curve, and then you see the results.png. The decrease in loss was steady for all three losses, but then again the precision and recall were still not showing any persistent trends or patterns of improvement. So there is that. And then if you see the results.csv for this training, I trained it for 50 epochs and I got a map score of, I guess, not even 0.3 again. So I moved on to another training session where I finally performed the all those augmentations. This was done with the oversampled dataset, and this was done with the augmented dataset. All the augmentation that I had done was already I already explained it in the script that I previously showed you, and this is the training. Yeah, so if you see over here, I actually didn't let it to finish. The training was going on pretty slow as it was training on 30,000 images and the speed was very much low. I am doing this on my local system, which is not very fast. It just has 4 gigabytes of graphics memory, so it is not that much, and it takes a lot of time to train. You can see loss decreased from 1.5 to this much, but it is not that great either. I actually used transfer learning. I retained the model that I had used by training, that I used in training on the oversampled dataset, and then that's why it starts from here, and this is the DFL loss. The precision was around 0.62 at some point, and even the recall was not that great. It was 0.22 at max, I guess, and the map score didn't reach even 0.25 this time. The map 50 to 95 scores were also very poor. It didn't even reach 0.2 this time. So I was getting pretty demotivated because of this, and so I finally thought of maybe researching a bit more about why this YOLO model is not performing so well. And then I came over this this forum where someone had asked a similar question, why he was not getting why most of actually he also saw that in his confusion matrix the most of the objects were actually being misclassified as background. So I went through the forum and I saw a person. He was actually this person, Stephen Charlett, and I guess he might be the author of this darknet model, which is utilized by all the YOLO models, like YOLO v5 and YOLO v8 are all contributions of his only. So let me just quickly find out who is Stephen Charlett. So seems like he's not the actual author of the darknet models, but anyway, he gave me a very important insight in this aspect, that if you see, if you reload this page, you might be able to pinpoint to that article. Yeah, so the question was, can I train a neural network using synthetic images, as I am doing? The answer is no. Or to be more precise, you will probably end up with a neural network that is great at detecting your synthetic images but unable to detect much in real world images. He also gave me a link to this video where he actually demonstrates this how his this model is actually working on detecting the, I don't know much about cards, but these designs on these cards and these numbers as well. So what he said was that the model in the YOLO implementation of this model, the model does not actually only focuses on the objects and the bounding boxes, it also focuses on the background, so that it learns where to find the objects. So that is how YOLO model works, and since it also focuses on the background, it might not be suitable for training on the synthetic images. So that's why the answer is no. So after doing this much training and all that stuff, I finally found out that this YOLO model cannot be used for this process. And the best metrics that I got while training all this stuff was I guess in this one. No, it might not be this one. Was it this one? Yeah, so car was being correctly largely classified as car only, so the best metrics was in the training 2 session, but then again the performance of model dropped as I continued to perform transfer learning, and even after performing so many augmentations and oversampling and every other technique that is possible while training this model, I didn't get much success. So, and let me just quickly show you how bad these models work on an actual image. This test script can do the job for us. Firstly, let me show you how the actual the pre-trained YOLO V89 model works on this image for inference. Yeah, so as you can see, this image actually has a truck, and in the background there is this motorcycle who has just the wheel part of the motorcycle is visible and nothing else. So the bounding box seemed to be fine. It could have been a bit over here to the right, but it is largely fine, and it should be a bit up here. And it is also misclassified as train instead of truck, and the confidence value is also just 0.33. So as you can see, even the pre-trained model is not working so great on the dataset that we have been provided with. So let me now just change this to some other weights. So let's try this with train 3. Yeah, so it is in runs, then detect, then weights, then best.pt. and now it is actually train 3, runs, detect, train 3. Yeah, so let's run the inference on this one. As you can see, the inference was much better. The confidence was 0.88 for this, and the bounding boxes is also so much better. the confidence is 0.88 and the classification, this is class ID, is also so much better. Now if you look at the actual labeling of this, you might be able to see that what the actual annotations were. Actually this image is night673.jpg, so let me just quickly search for it. night673.jpg, and then search for it over here in the labels. I don't know if that was in train or val. Yeah, so it was in val only. So this was so there is basically two labelings, and our model is able to detect only one of the labels, and the class ID is 2 and 7. So let me see that in the data.yml. The second one is 7th one is truck, and if it is 1 2 3 4 5 6 7, yeah, so seems like our class ID starts from 0 and goes all the way to 14th. 0 1 2 and then 3 4 5 6 7. So this labeling is fine, but I don't think even I was able to see any auto in this. There is no auto, I guess, in this picture, but it is labeled as class ID 2 over here. So I guess the issue that guy opened was also true. The labeling seemed not to be correct, as this class ID 2 is nowhere to be found in the actual image, but it is there anyway. So these are some of the other discrepancies that might have led to such poor performance. And yeah, and now let me just try doing the inference with the fourth training. As you can see, the bounding box went burr, and the bounding box, instead of limiting itself over here, it goes all the way to the to above the truck's image, and the confidence is much lower. So the performance is poor in that sense. And then there is train 5, and the confidence even gets worse with just 0.38 of confidence, and the bounding box remained equally bad. And then let's now finally try train 7 that I had trained at the last, and as you can see over here, not even one bounding box is to be found, and hence the augmenting the dataset didn't work. So my conclusion training this YOLO V8 model was that the dataset that we have been provided with was not good enough, or maybe the YOLO V8 model is not specifically designed to be trained on synthetic datasets. So this compatibility was not supposed to be good, and it is not good. Yeah, so there's that. So I'll be dropping this idea of training the YOLO V8 model further, but the best I got while training this was during the train 3, I guess. Let me just check it once again. Yeah, so confidence was even the most in the third training session, and the bounding box and everything is fine here. So this is the best we got, the train 3. You can find it over here, and as we also see, the confusion matrix was even the best for this one only. Yeah, so I will just rename it as the best one just to remember that it is the best one. Yeah, so we have done training the YOLO V8 model, and now moving on to the FDET model. Now this FDET model actually has a very different implementation as compared to the YOLO V8 models. I was training YOLO V8 model in PyTorch, but this AVD FDET model is actually implemented. This particular API is implemented in TensorFlow. So I just formatted, converted the previous dataset into a format that was compatible with this efficient DET model, and so I just made these 3 directories. This one contained annotations, annotation files, which were in .json format for train and val instances, and this one had the val images. Yeah, so basically this annotation, how you might be thinking how I got these .json files. I had to make this using a script called this one, create TF record. You can even find this if you clone the FDET model from the TensorFlow Jew repository, and this script was there only. I had to modify it a bit. Let me just open these scripts now so that I can show you better. Yeah, so this is the script. These are the function that I had to use, and this is it. So this was the script that I used for converting the labels to .json format in order to actually train the model. And these are the checkpoints. These checkpoints are actually the pre-trained models that I got from, again, the TensorFlow Jew repository, where all the models for object detection and everything else are placed. This is the directory that I actually cloned from the Jew repository. Most of the models are in this directory called research. And this is let me show you the pipeline.config. So this is the config file that actually specifies everything about training the model. Yeah, so batch size was 4 only, because even I was not able to even keep the batch size 6 because the memory utilization was so much while training this model. It is not that much efficient and optimized, and moreover I also got another error in which the optimization function where the graphs were actually supposed to be optimized for training on a system was not working fine, so I had to disable it, and the performance was even worse. So I had to go with batch size of 4. And even after then, the total number of steps I have specified 3 lakhs. So it is too much, and I actually calculated how long it would take, and it just showed me that it might just take 1 week of training on my local system in order to train this model for 30,000 steps. So that's pretty big, pretty long duration for training this model. And also, in order to run the training script, I had to do all this, as I usually establish my workspace environments in Anaconda. So I just if I tried to do this in the command prompt every time, it was very much lengthy, and I had to remember all the commands. So I just made a script that had all these commands listed here one by one, and running this command just starts the training process. And I didn't check about the performance of this. Yeah, so and this is the readme.md file that is actually used in the script file for starting the training process. So I tried training YOLO V8 model, YOLO V5 model as well as Efficient models, and I presented the findings that I found in this video, and I hope I will find a much better solution to this problem, this challenge, as except YOLO V8's third training, not many of them were that much good, but let's hope for the best. And I guess that is it for this video. Thanks.